Ever stop to think about the spaces between whole numbers? I mean, we use numbers for everything, like counting, measuring, even music. But what about those in-between values? What happens there?
It's like that moment you realize there's a whole universe between, say, the keys on a piano. We're so used to whole numbers, but the reality is they only tell part of the story.
Exactly.
Yeah.
And that's what we're looking at today, Ray.
Yeah.
We're taking a deep dive into the world of rational numbers,
Yes.
exploring how they fill those gaps
Yes.
and why they even matter. We've got this fascinating math chapter to dissect, and trust me, this is way cooler than how they taught it in school.
Absolutely. And it's like those integers, those positive and negative whole numbers, they're just wearing a disguise, really. They're rational numbers, just with a denominator of 1 hiding underneath.
Okay, now I'm intrigued, but let's back up a bit for our listeners.
Sure.
The chapter starts with those basic number systems.
Yeah.
Counting numbers, whole numbers, integers.
Right.
We use them every day,
Yeah.
but they can't quite capture everything, can they?
Right. Right. Think about it. Integers are great for representing opposites. Profit and loss, degrees above or below freezing, but what happens when we need to be more precise?
Like trying to measure a piece of fabric that's not quite a whole inch.
Exactly. Or imagine you're a marine biologist charting the ocean floor. You're 750 meters below sea level. That's a negative situation, sure, but you can't neatly represent that depth with just integers, right? You need something more nuanced, something that can handle those in-between values.
And that's where our friends, the rational numbers, come in.
Precisely.
All right. So let's unveil the mystery. What exactly is a rational number?
In simple terms, it's any number that can be expressed as a fraction, where both the top, the numerator, and bottom, the denominator, are integers, and that denominator isn't 0. Think of it like a delicious pie. You've got your numerator, the number of slices you have, and your denominator, the total number of slices the pie was cut into.
Okay, so it's like fractions are the superheroes of the number world swooping in to represent those in-between values. But the chapter also mentions decimals. Do those fit into this whole rational number picture?
Absolutely. Decimals are just another way of expressing those pie slices, those fractions. Think of 0.5. It's just a stylish way of saying 12, which fits our rational number definition perfectly. Even those decimals that seem to go on forever, like 0.3333 repeating, can be represented as fractions, in this case, 13.
So decimals are like the Clark Kent to a fraction's Superman, same power as a different outfit.
I like that analogy. And speaking of hidden identities, remember how we said integers are rational number in disguise? We can write any whole number as a fraction with a denominator of 1. So 5 becomes 5110 becomes -101. They're all part of the rational number club.
It's like uncovering a secret society of numbers.
Hmm.
But then the chapter dives into this standard form thing. What's that all about? Sounds very official.
Think of standard form as the secret handshake of rational numbers. It's how mathematicians make sure they're all on the same page. Basically, we express the rational number with a positive denominator, and we simplify it so the numerator and denominator don't share any common factors other than 1.
So it's like finding the most elegant way to write the fraction its most streamlined form.
Precisely. Imagine you're describing a recipe. You could say, use 2 cups of flour for every 1 cup of sugar. Or you could say, use a 2.1 ratio of flour to sugar. The second way is more concise, right? That's what standard form does for rational numbers.
Give me an example. Show me how this simplification works in action.
Sure. Let's say you have the rational number -1220. To get it into standard form, you find the greatest common factor of 12 and 20, which is 4. Divide both the numerator and denominator by 4, and you get -35. Much cleaner and easier to work with.
So it's like we're distilling the rational number down to its essence. But why is this standard form so important?
Because it makes comparing and doing calculations with rational numbers much smoother. It's like having everyone speak the same language. Speaking of which, once we know how to write rational numbers in this standard form, where do they actually fit in the grand scheme of things? Let's picture them on a number line.
Ah, the good old number line. I remember spending a lot of time with those in school. But I'm guessing plotting rational numbers is a bit more nuanced than just marking whole numbers.
You're right. It's not quite as straightforward, especially when we start dealing with negative rational numbers.
Okay, now we're getting to the part where my brain usually starts to hurt a little. Are we talking about those mind-bending negative fractions where bigger denominators mean smaller pieces, but since they're negative, those smaller pieces are actually, like, bigger?
You're exactly right. It's like looking at those shrinking potions in fantasy movies. The smaller the amount, the more potent the magic, or in this case, the larger the negative value. For example, let's say you have Menninger 14 and Menninger 12. If we were dealing with positive numbers, 14 would be smaller than 12. But because they're negative, Negative 14 is actually closer to 0 on the number line, making it the larger of the two.
Okay, I think I just had one of those aha moments the chapter promised. It's counterintuitive, but it makes sense when you think about it visually on that number line.
And that's the key takeaway here. Visualizing rational numbers on the number line can really help you grasp their relationships and values. But even without the number line, we can compare rational numbers by using what we learned about standard form.
Right, so if we have two rational numbers in standard form, we can just compare them like we would any other fractions.
Exactly. If they're both positive, it's pretty straightforward. But when negative rational numbers are involved, we just have to remember that reverse the order trick we talked about earlier.
Okay, that's a good reminder. But what happens when we have a mix of positive and negative rational numbers? Do we need some kind of super complicated formula?
Not at all. That's actually the easiest scenario. Positive rational numbers will always be larger than negative ones. Think about it in terms of temperatures. Anything above 0 degrees will always be warmer than anything below 0.
Oh, that makes perfect sense. So no matter how big the denominator of a negative rational number, it will always be smaller than any positive rational number, even a tiny one.
You've got it. And here's another cool thing about rational numbers. Sometimes they might look different, but actually represent the same value. Think of it like ingredients in a recipe. 12 cup of sugar is the same as 24 cup of sugar.
So even though they're written differently, they result in the same amount. Does that happen with rational numbers too?
Absolutely. Take Magnus 615 and Neginus 25, for example. They look different at first glance, but if you simplify them both to standard form, they both become negative 25.
That's a great reminder to always simplify whenever we can. Okay, now for the mind-blowing part. The textbook talks about how there are an unlimited number of rational numbers between any two rational numbers. This is where my brain starts to melt a little.
I know, right? It's a mind-bending concept. We can keep finding more and more rational numbers between any two others, no matter how close together they are. Think of it like zooming in on a fractal. You keep discovering new patterns and details no matter how far you go.
It's like those Russian nesting dolls. Just when you think you've reached the smallest one, there's another one hiding inside. So how do we actually find these hidden rational numbers?
One way is to keep increasing the denominators. For example, let's say we want to find rational numbers between 12 and 34. We can rewrite them with a common denominator of 8. So we have 48 and 68.
And then we can multiply both the numerator and denominator by the same number to find more rational numbers in between, right?
You got it. We could multiply by 2 and get 816 and 1216, or by 10 to get 4080 and 6080, and so on infinitely. It really highlights that rational numbers don't just fill in the gaps between whole numbers. They create a whole new kind of density on the number line.
So we've got these rational numbers fitting snugly between integers, representing all sorts of values we couldn't express otherwise. It's like unlocking a secret code to understanding the universe in a whole new way.
That's a great way to put it. Rational numbers may seem abstract at first, but they have incredible real-world applications, from measuring distances and calculating proportions to understanding music theory and programming computers. They're everywhere.
It's amazing how something so fundamental can have such far-reaching implications. And on that note, we'll leave you with something to ponder. If we can fit an infinite number of rational numbers between any two others, does that mean there are more rational numbers than there are whole numbers? It's a question that has puzzled mathematicians for centuries, and it's something to keep in mind as you explore the infinite and fascinating world of rational numbers. Thanks for joining us on this deep dive.